everyone, today a video on amines and specifically an introduction to them and their properties. So amines are a group of compounds that are derivatives of ammonia. Remember that ammonia is NH3. And it's where we've taken this ammonia and we've replaced one or more of the hydrogen atoms by an alkyl or an aryl group. And they're very reactive compounds and they're very useful as intermediates in synthesis. They're very useful for making lots of other compounds. Now we can classify amines like we classify alcohol in terms of primary, secondary and tertiary, but the way we classify them is slightly different. In alcohols, the primary, secondary and tertiary refer to the number of substituents on the carbon atom that was bonded to the OH group. In amines it's slightly different, that the primary, secondary or tertiary refers to the number of substituents, the number of R groups, carbon-based groups, that are directly bonded to the nitrogen atom. So a primary amine has one R group directly bonded to the nitrogen. A tertiary amine has three R groups directly bonded to the carbon atom, for example. In terms of naming them, our standard IUPAC naming rules apply. Primary amines have the general formula of RNH2, where R represents the alkyl group. They're named using the suffix amine at the end of whatever the carbon chain length is, so we always have to look for our longest carbon chain. Remember that we want to make sure that the numbers are the lowest. If we have any other substituents on that carbon chain, we have to number them. If we have multiple of them, use di, tri, tetra, for example. Secondary amines have the general formula of R-NH, where the R- just represents a different alkyl group. Of course, it could be the same. And tertiary R-R-N. And different substituents are written in alphabetical order. So if we look at the examples on the right, the first example is simply methylamine. So the way we name them is we take our chain length, which in this case is 1 carbon long, so it's based off a methyl length chain, and then it's an amine, so we use the suffix amine. So it's methylamine. Likewise, if our carbon chain length was 3 carbons long, that would be propylamine. Now, if the amine is in the middle of the chain, we can start to number where the amine group is. So, for example, the example there on the far right is propan-2-amine. Or another way to name it is 2-aminopropane. And sometimes you'll see also that if the molecules have another functional group in them, for example a carboxylic acid group as well, that the NH2 group isn't named using the suffix amine but used the prefix called amino. Now, that's for primary amines. When we look at secondary or tertiary amines, it's a slightly different naming convention. Our longest chain is still the kind of ending of the name. So the example at the bottom left, the longest chain there is the ethyl chain. So the name still ends with ethylamine. But we also have to name other substituents on the nitrogen. And the way that we write this is simply by putting N and then the length of the chain that's attached. So in this case, we have a methyl group also attached to the nitrogen. So this is known as N-methyl-ethylamine. The example to the right of that, this is now a tertiary amine. We have an ethyl group attached, we have a methyl group attached, and then we have a propyl group attached. So the same thing goes for naming it. We look for our longest chain. In this case, the longest chain is the propyl group. So the ending of the name is propylamine. And then we have to name the other substituents using that N terminology again. So it is N-ethyl, N-methyl propylamine. Note how that we've done that in alphabetical order. Remember that we name things alphabetically, not numerically. For a final example, imagine there were 2 methyl groups on that final example, not an ethyl and a methyl. That would be N-N-dimethyl propylamine. So much like if we have, for example, 2 methyl groups, we'd have to name it as 2,2-dimethyl, for example. We name the N bit twice, N-N-dimethyl. So ammonia, NH3, if you remember, is a pyramidal molecule, and it has bond angles of about 107 degrees. If we consider our ammonia molecule, we have a lone pair, and then we have 3 NH bonds. So there's 4 actual pairs of electrons. So our pseudostructure would be based off a perfect tetrahedron, bond angles of 109.5. But because we have that lone pair, that squeezes the bond angles down slightly because lone pairs repel more than bonding pairs. And so we end up with a bond angle in ammonia of about 107 degrees. And now it's not a tetrahedral shape, but a trigonal pyramidal shape. And amines generally keep this basic shape, because remember, all we've done from getting from ammonia to an amine is replace the hydrogens with carbon groups. Now, amines are polar molecules. Primary amines can hydrogen bond using their NH2 groups, and so they can hydrogen bond to each other, or they can hydrogen bond to other polar molecules that can, such as water. Now, nitrogen is less electronegative than oxygen, and so the hydrogen bonds are not as strong as those found in alcohols, and so the boiling points are slightly lower than the corresponding sort of similar molecular mass alcohol. However, because nitrogen is less electronegative than oxygen, that lone pair is less tightly held. It means that they're better nucleophiles. They're more available to give that lone pair away and react, so they're much better nucleophiles than alcohols, which makes them, again, very useful from a synthetic point of view. Shorter chain amines are gases at room temperature. Slightly longer chain ones tend to be volatile liquids, and of course, as we keep on going and ongoing in terms of increasing molecular mass, we have greater van der Waals forces, along with some potentially dipole-dipole forces, and of course hydrogen bonding in some cases. And they have characteristic fishy smells. So short-chain primary amines are very soluble in water. They can hydrogen bond to the water, and so that makes them very, very soluble. Remember that when we draw out pictures of hydrogen bonding, we need to show our lone pair, we need to show our partial charges, delta negatives, delta positives, and show the actual hydrogen bond with a dashed line. Now, most amines are also soluble in slightly less polar solvents as well, but phenylamine, that's an amine where we've replaced one of our ammonia, where we've replaced one of our hydrogens now with a benzene ring, essentially, is not very soluble in water because we have this large non-polar benzene ring, and that can't form hydrogen bonds, and that kind of dominates the polarity of the molecule. So amines, like ammonia, have a lone pair of electrons, and this can be used to form a bond with a proton, an H+ ion, in which case we say the ammonia is acting as a base, accepting the proton, or that lone pair can be used to form a bond to an electron-deficient atom, quite often a carbon atom. And in this case, it's acting as a nucleophile, an electron pair donor. So looking at amines reacting as bases, well, amines are bases and they can accept a proton, and they will react with acids to form ionic salts. And these are ionic compounds that will crystallize as we evaporate off the water. Now, aryl amines are relatively insoluble, as we said, because of that very large benzene ring that is also attached, but they will dissolve in excess hydrochloric acid. And the reason for this is because if we react HCl with our aryl amine, for example, phenylamine as shown at the bottom here, acts as a base, accepts a proton from HCl, and we end up forming this phenol ammonium chloride salt. Now, because it's an ionic salt, it's therefore water soluble. If we took that salt and we added a strong base, for example, sodium hydroxide, then this will remove the proton from the salt. Again, it's just the reverse, essentially another acid-base reaction. Removes the proton from the salt, and it will regenerate the insoluble amine. So typically these amines are insoluble. By making the ionic salt, we can make them soluble. So if we think about, again, them acting as bases and importantly the strength of these bases, essentially it depends on how readily it can accept the proton. Now, both ammonia and amines have a lone pair that will obviously attract a proton, but we can also start to think about in our amines, it depends on what kind of groups we have attached, what kind of groups we've replaced these hydrogen atoms with. So alkyl groups release electrons away from the alkyl group and towards the nitrogen atom. And this is something called the inductive effect, and you'll have seen this before if you've seen the alkene set of videos. Now, this effect essentially means that alkyl groups kind of push their electrons away from themselves and onto, in this case, the nitrogen, and this increases the electron density on the nitrogen atom. If we increase the electron density on the nitrogen atom, well, this makes it a better base. It makes it a better electron pair donor. There's more electron density there. It's more attractive to protons. And so by putting alkyl groups on there, we've made it a better base. So primary alkyl amines are stronger bases than ammonia. Secondary alkyl amines, where we've now got two alkyl groups and hence two inductive effects, are therefore even stronger bases than the primary alkyl amines. However, the important distinction is that tertiary alkyl amines are not stronger bases than secondary. Even though there's now three alkyl groups, so three inductive effects, which you think would massively increase the amount of electron density, these tertiary alkyl amines are much, much less soluble in water. There's now much, much more carbon non-polar part of the molecule, which means they're far less soluble in water and less able to act as a base easily. On the other side of the coin, we have aryl groups, phenol groups, benzene rings, that kind of stuff, where these withdraw electron density. If we think about having a benzene ring attached to our NH2 group, we have this region of very high electron density, and this wants to pull electron density towards it. And so this essentially is the inductive effect, but now towards the benzene ring rather than away from it, like we saw with the alkyl groups. And this is because the electron density can overlap with the delocalized pi system of the benzene ring. Essentially almost adds to the aromaticity. And so the nitrogen is therefore less electron rich. We can think of our electron density being kind of taken away from the nitrogen. And so if there's less electron density, it's a less strong base, a weaker base than ammonia. And so generally at the top, we can see here that we have our phenyl amine, we have our ammonia, and then we have our alkyl amine. And generally, as we go from left to right, the basicity increases. And likewise, if we consider ammonia going to a primary amine, going to a secondary amine, well, the basicity increases. But of course, remember, the tertiary amine is actually not the strongest of those bases because it's less soluble in water. So, time to have a go at some questions. If you want to have a go, pause the video and the answers will be on the next slide. So the first one is to name the following structures of those amines, then to write the equation for 4-nitrophenylamine with nitric acid, and if the product is soluble, and then to say whether the following compounds are better or worse bases than ammonia is. So the first question was to name the following structures. So for the first one of these, remember that when we name them, we always have to look for our longest carbon chain. Our longest carbon chain in this example is 4 carbons long, starting at the carbon where the NH2 group is attached and working from right to left. So it's 4 carbons long, so we know that we're going to end with the name butylamine. Remember that we use the suffix amine, so butylamine at the end. And then we need to have a look at what other substituents we have attached. So we have an OH group, and we have 2 ethyl chains as well. Now, remember, we always want the lowest numbers, so we could number from left to right. But going from right to left is going to give us smaller numbers because the amine is going to end up being on the first carbon. Our ethyl groups also end up being on the first carbon, and our OH group ends up being on the second carbon. That's a much lower number system than if we went the other way around. The only other important thing to note here is that while we have an alcohol, which we'd normally denote with the suffix -ol, because we have our amine here, that sort of takes priority in the functional group naming. So the amine is the suffix, and we have to use the prefix of hydroxy for the OH group. And then we're able to remember that we name alphabetically and not numerically. So the name of this is 1,1-diethyl-2-hydroxybutylamine. And remember that if we have multiple of them, we have to use the di terminology, and we also have to make sure that we number every single one. So not just 1-diethyl, but 1,1-diethyl-2-hydroxybutylamine. The second example, again, look for the longest chain. In this case, again, it's 4 carbons long, starting from the carbon directly attached to our nitrogen and going from right to left. So again, we're going to end with butylamine. We then need to have a look at the other substituents. So we have a chloro group attached onto our carbon chain. And we also have here a tertiary amine, so we have other substituents attached to the nitrogen. Now the one that we use at the end of our chain is the longest chain, so the butyl chain there goes at the end, butylamine. But we also have an ethyl group and we have a methyl group attached as well. So then we just have to make sure that we name alphabetically. We can number from left to right or right to left again, and again the smallest numbers we get from going from right to left. And so the name of this is 2-chloro-N-ethyl-N-methyl-butylamine. And remember that when we have extra substituents on the nitrogen, we have to use this N prefix. So the second question was then to write the reaction of the 4-nitrophenylamine with nitric acid. This is just an acid-base reaction. So our nitric acid is acting as the acid, our phenylamine acting as the base, accepting a proton. So we end up forming our ionic salt. And in this case, yes, because the product is an ionic salt, it would be soluble in water. If we want to regenerate our insoluble amine, we'd have to add some strong base such as sodium hydroxide. And then finally, the 2 examples here was to ask whether they were better or worse bases than ammonia would be. So the first example here, you can see you have this, this very, very electron withdrawing group, not only do we have a carbonyl group, which is electron withdrawing, you can imagine you've got that delta positive carbon right next door to it, but we also have this CF3 group, and obviously fluorine is the most electronegative element. That's also very electron withdrawing as well. So essentially what we're looking for is, well, that carbon that's directly attached to the NH2, that's very delta positive. We've got two very electron withdrawing groups attached to it. That's going to want to attract the electron density from the NH2, the lone pair from the NH2. And so like when we had our phenylamines, it takes away electron density from the NH2 group. So this would actually be a worse base than ammonia. On the other example, we have this bromine group attached to our NH2, and this actually ends up being a better base than ammonia. And the reason for this is because bromine itself has lots of lone pairs on it that can actually be electron releasing by something called induction. So essentially the bromine can kind of almost just sort of push its electrons towards the NH2. So it's a better base than ammonia because we've increased the electron density on the nitrogen atom. So thank you for watching. You can find a lot more videos like this on my YouTube channel. If you found this video helpful, please leave a review on one of my tuition websites. I offer online tuition for chemistry, so please check the tuition pages if you're interested in that. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.